Yeah, thanks very much, Katja, and thank you for the invitation. It's a great pleasure to participate in this very nice event, and it's great to see so many familiar faces from all around the world. Right, so before I start, let me make a short advertisement. It's about a Finnish mathematics journal, Annales Fennici Mathematici, which was founded in 1941, and it had a strong focus on complex analysis. But somehow last year it was rebooted, and now it covers the main fields of mathematics in Finland, including inverse problems. And I'm one of the editors, and the journal is looking for submissions. And some features of the journal is it's diamond open access, meaning it's free for both readers and authors. And also for all published papers, the journal provides abstract in Finnish language. And this is something which I can guarantee no other journal will give you. So please consider submitting papers. Okay, so the title is Free Boundary Methods in Inverse Scattering. And it's somehow basically about a new approach to certain problems in inverse scattering that have been studied in recent years. And the structure is quite basic. So first I'm going to introduce the basic problem and give some motivation for these inverse scattering problems. Then I'm going to state the number of results. And in the final part of the proof, going to say something about the arguments for proving these results. Okay, so let's start motivating this problem with the Calderón problem, which originates in geophysics in the 1920s for finding oil inside the Earth, where the idea is to put electrodes on the surface of the Earth and then put some voltages on these electrodes, and then there will be electrical current going through the Earth. And one is going to measure the currents on the surface by using the same electrodes. And with these kinds of electrical measurements, one wants to find out what is inside the Earth, in particular if there's an oil deposit or not. And this is called the Calderón problem because of the fundamental work of Alberto Calderón, who gave a very elegant mathematical formulation and introduced the method of exponential solutions, which has been influential in this problem. And this is also used in medical imaging. So in the picture on the left, you can see one of the commercial devices, an electrode belt manufactured by Centec, which is used for monitoring the lungs of a patient. And in Finland, we are somehow applying this electrical impedance tomography to detection of brain stroke. The idea is that in an ambulance, you could quickly decide the type of the brain stroke that the patient is having so that you can give the correct medicine. And the model here who is displaying the latest fashion in electrode hats is Samuli Siltanen from Helsinki. So mathematically, the Calderón problem is modeled by the conductivity equation, divergence gamma W equal to 0 in omega. You fix Dirichlet data F on the boundary. Omega is a bounded smooth domain and gamma is a positive L infinity function, the electrical conductivity. And the idealized boundary measurements are given by the Dirichlet to Neumann map, which is the map that takes any Dirichlet data F into the corresponding electrical current on the boundary, which is the gamma times the normal derivative of U. So it basically maps the Dirichlet data to the Neumann data. And this corresponds to having infinitely many measurements. So you can put infinitely many voltages F on the boundary and measure the corresponding currents. And the inverse problem is if you know these infinitely many measurements, you want to recover the conductivity gamma. And of course, there's a huge literature on this problem. And some of the main results are due to Sylvester Ullmann in 3 and higher dimension, and Nachman Astela-Päivä in 10 2 dimensions. These are related to uniqueness for determining the conductivity gamma from the map lambda gamma. But of course, in practice, one can only make finitely many measurements. So this is what people do computationally. So you know finitely many measurements, lambda gamma f1 to lambda gamma fn for some capital N. And there has recently been also rigorous work on these finitely many measurements, for instance, these papers by Alberti, Santacesaria, and Harrach. Actually, in this talk, we are interested in kind of even more extreme case, which is the single measurement case. So we know the electrical current lambda gamma f only for a single function f. And of course, this may not work for any function f. For instance, if f is identically 0, then you are not going to get any information about the conductivity. So you might want to look at some well-chosen single measurements f, or Dirichlet data f, or you could ask what can you determine if you have an arbitrary Dirichlet data f which is not identically 0. Okay, and then the first thing to observe in the single measurement case is to do a dimension count. So the data, which is the measurement lambda gamma f for a single f, it's just the normal derivative on the boundary. It depends on n-1 variables, whereas the unknown function gamma in general depends on n variables. So this inverse one would be formally underdetermined. And indeed, one can show that you cannot determine a general function gamma from only one measurement. So what one could do is one could assume some a priori knowledge on this gamma. And one popular case is to consider conductivities which are related to some obstacle. So you have a subset d of omega, which is called the obstacle. And then you have a conductivity function, which is 1 outside of the obstacle and which is equal to some constant k, which is not equal to 1 inside the obstacle. So you have a conductivity which somehow jumps at the boundary of the obstacle. And you can ask whether you could determine the shape of this obstacle from the single measurement. And now if this set D is not very wild, then the boundary would be n-1 dimensional. So this inverse one would be formally determined. And there are a number of results on this, this problem. So let me just formulate an open question, which is classical, but in this precise way, it was formulated by Alessandrini. It's asking if n is equal to 2, and if you have a well-chosen boundary data f, in particular, f satisfies Radon's condition from the Radon-Kneser-Choquet theorem. So f is complex valued and it's a homeomorphism from the boundary of omega into the boundary of the unit disk. Does a single measurement lambda gamma f determine the obstacle D? So this is known if D is a simply connected polygon. It's a result by Salo. And Alessandrini has a prize on this problem. So the person who solves this can look forward to receiving 3 bottles of Friulano wine. Okay, so let's get closer to inverse scattering, which is more the topic of this talk. So we are now looking at the Schrödinger equation minus Laplacian plus q of u equal to 0 in omega. You fix Dirichlet data f. Omega is a domain, q is an elephant function, the potential. Boundary measurements are given again by the Dirichlet Neumann map lambda q, which takes the Dirichlet data f into the Neumann data, the normal derivative u on the boundary. And here I assume that 0 is not the Dirichlet eigenvalue of this, this problem. And again, the inverse problem with infinitely many measurements would be given the measurements encoded by the map lambda q. You want to recover the function q. And again, I want to look at the single measurement case. So you want to recover something about the potential q from the measurement lambda qf for a single function f. Again, this is formally underdetermined, but you can again look at the obstacle case. So you have a so-called penetrable obstacle D. It's a set which is somehow buried inside omega. And then you have a potential q, which is 0 outside of D, and it jumps at the boundary of D. So q is equal to h times the characteristic function of D, where the contrast h is a function which is non-zero at the boundary of D. So there is also the problem of looking at an impenetrable obstacle. So in this case, you would have the Schrödinger equation outside of D, and then you have some Dirichlet or Neumann boundary condition on the boundary of D. And I'm not going to discuss those kinds of results in this talk. So the inverse problem would be given the single measurement lambda QF for a fixed Dirichlet data F. You would like to recover something, at least about the obstacle D. Okay, so again, so the inverse problem would be given lambda QF for a single function F, you want to recover the obstacle D. And there is one case where this is not possible. So we say that the obstacle D is invisible for the particular choice of Dirichlet data F if lambda QF is equal to lambda 0 F for some contrast H. So Q was equal to H times chi D, where H was the contrast. So this would be saying that if you have an obstacle like this, then for this particular Dirichlet data F, this obstacle D with this contrast H would look like empty space. And of course, then it cannot be recovered from the knowledge of lambda QF. So the main question of this talk will be the following. So which obstacles D can be invisible for some choice of Dirichlet data F and for some contrast H in this obstacle D? And this is different from this invisibility cloaking construction. So in cloaking, you typically want that your coefficient is invisible for all possible Dirichlet data F. So here I'm just looking at the single measurement, and I'm asking whether the set D can be invisible for some choice of F. Okay, and then we can also ask similar questions in the inverse scattering case. So now instead of a bounded domain in Rn, I'm looking at the equations in all of Rn, and the equations could be, for instance, minus Laplacian minus k squared eta of x applied to u equal to 0. So this would be corresponding to acoustic scattering, or minus Laplacian minus k squared plus v of u equal to 0, which corresponds to quantum scattering. So here k is a fixed frequency, and eta is an index of refraction, is assumed to be 1 outside of the obstacle D, and it jumps on the boundary of D. And this capital V is of the form H times chi D, where H is non-zero at the boundary of D. And in the scattering problem, we have an incident wave U0, which is a solution of the free Helmholtz equation, Laplacian plus k squared U0 equal to 0 in Rn. For instance, it could be a Herglotz wave or a plane wave. And then you look at the solution of one of these equations, which can be written as U0 plus U scattered, and this U scattered is assumed to be outgoing. It satisfies the Sommerfeld radiation condition. And then this solution, you will have a far field pattern, which is a function on the sphere, denoted by U infinity. So in inverse scattering, the question would be as follows. So which obstacles D can be invisible for some particular incident wave U0 and some contrast H, in the sense that the scattering measurement, the far field pattern U infinity is equal to 0. So this means that if an obstacle is invisible, then it's possible to find some incident wave so that the obstacle is not going to produce any scattering response at all. So this far field pattern is equal to 0. And this is closely related to the concept of non-scattering energies and interior transmission eigenvalues, which have been popular topics in inverse scattering theory recently. Okay, so let me now recall some earlier results on this problem. So there are many papers which have proven results stating that corners always scatter in one sense or another. So these kinds of results are saying that an obstacle D can never be invisible for any choice of incident wave. if there's some kind of corner point in the boundary of this D. And some of the rigorous analysis of this phenomenon was studied in this paper of Blåsten, Päivärinta, and Sylvester in 2014. It's a very nice paper with many interesting ideas. And the result was that if the obstacle D has a 90-degree corner, so part of D is part of a cube, it's kind of a very rigid type of 90-degree corner, then this obstacle D can never be invisible for any contrast or for any incident wave. And there have been many subsequent works. For instance, if n is equal to 2, with Päivärinta and Vesalainen, we show that any corner which is less than 90 degrees will always scatter. And actually these two works and many others are based on using complex geometrical optic solutions, which is a popular method in the Calderón problem, and some analysis of Laplace transforms. So there's another method introduced by Elsten and Hu, which is based on the theory of boundary value problems in corner domains, using some special weighted spaces which are relevant for that case. And they show that if the dimension n is 2 or 3, and if this obstacle D has a curvilinear corner or edge, then it can never be invisible. So these kinds of corners also always scatter. And there's a sequence of works by Blåsten and Liu and co-authors. One of their results is saying that if D has high curvature points, then you have some kind of scattering. And the idea here is that if you have a corner point, then the curvature is infinite at the corner point. But if you have a point where the curvature is very high, then you have some kind of lower bound for the far-field pattern. And all of these results are just saying that if you have a corner point, then the obstacle D can never be invisible. But it turns out that one can use these corner scattering results to prove also uniqueness results in single measurement inverse problems, which was the motivation that I started with. And a typical result is saying that if the obstacle D is a convex polygon in 2D, then it can always be determined from a single measurement, no matter what incident wave you use. Many people have worked on this. In the other direction, there were very few examples of obstacles that can be invisible. So there's classical work by Colton and Monk, which implies that balls can be invisible. So you can always, if you have a ball, then you can find a contrast, so that some incident wave will produce zero scattering response. And there's kind of similar or somewhat related work by Gale, Redman, and Hassel, where D is a union of balls. So if you are looking at this list of results, it still looks quite mysterious which obstacles D can be invisible and which cannot. And so what I'm going to discuss next is kind of a new approach based on free boundary methods, which will somehow shed light on this issue. Are there any questions at this point? Can you hear me well?
Yes.
Okay, great. Okay, if not, then let's move to the second part. So the main results. The new observation is that the boundary of an invisible obstacle can be interpreted as some kind of free boundary. So this observation was first made by Ciccone and Vogelius, and a little bit later in a paper of myself and Charles Golian. So below you can see a photo that I took last winter from the lake, which is next to my university. And the resolution is not very good, but you should be able to see some interfaces between water and melting ice. So this is one example of a free boundary which appears in nature. And it turns out that the boundary of an invisible obstacle has a kind of slightly similar features. It will not be exactly this kind of free boundary, but it would be a free boundary in an obstacle type problem. And it turns out that these kinds of results were quite classical in the single measurement Calderón problem. So this idea was introduced by Alessandrini and Isakov in the 1990s. But it seems that this connection to free boundary problems was somehow missed by people working on corner scattering, including myself. But once you make this connection, then you can use powerful methods from the free boundary theory of PDEs in order to say something about these invisible obstacles. Okay, so here is a slightly technical slide, but I'm just collecting the kinds of assumptions that are sufficient for these main theorems. So omega will be a bounded domain in Rn, and k will be a fixed frequency. It can be also 0. D will be the obstacle. It's an open set whose closure is contained in omega, as it satisfies some topological conditions. For instance, D and its complement should be connected, and the interior of the closure of D should be equal to D. So these kinds of sets are sometimes called solid domains. So this topological condition excludes the possibility of having holes in the obstacle. And this second condition is going to exclude obstacles like the slit disk, which are somewhat pathological in these settings. And also in some of these results, I will need a non-resonance assumption that the Dirichlet problem for Laplacian plus k squared in D is well posed. Okay, and so I denote by U0 or U0f the incident wave, and by this I just mean that it will be the solution of the Helmholtz equation Laplacian plus k squared U0 equal to 0 in omega, U0 equal to f on the boundary of omega. So this is the incident wave in the boundary case. But all of these results apply to scattering, so we can also take omega equal to Rn, and then this U0 f would be the Hergott's wave associated with the function f on Sn-1. So the definition of Hergott's wave is in the footnote. Okay, so let's go to the results. The first theorem, which is joined with Chagolian, is saying that if the obstacle D has real analytic boundary, then D will be invisible for any Dirichlet data f such that the incident wave is positive on the boundary of D. So so not just balls, but any set with real analytic boundary will be invisible for some Dirichlet data. And this should be read in such a way that for any f such that the incident wave is positive on the boundary of D, you can find some contrast H so that you have invisibility with respect to this contrast. And the construction gives contrast H which may have varying sign. So in this acoustic scattering application, you would like to have H with a fixed sign. So this, at least here, we don't get. But anyway, this is saying that any obstacle with real analytic boundary might be invisible. And then the question is, are there other obstacles that could be invisible? So we saw already in these corner scattering results that if you have some kind of corner point, then the obstacle is never going to be invisible. But it turns out that there are some obstacles with some boundary singularities that can still be invisible. So the second theorem is with Cole, Larson, and Chagolian, and it's saying that if D is a quadrature domain for the Helmholtz Laplacian plus k squared, then D is invisible for any Dirichlet data f such that you have this positivity condition. The incident wave is positive on the boundary of D. So what is this quadrature domain? So this is a classical notion in complex analysis in the case where k is equal to 0, so for harmonic functions. So in our case, we say that the set D is a quadrature domain if there is a mu, which is a distribution compactly supported inside D, such that the following holds. So if you take any solution W of the Helmholtz equation in D, which is in L1 of D, then the integral of W over D is equal to the pairing of mu and W. So it's somehow saying that you can evaluate integrals of solutions W by evaluation with this compactly body distribution in D. So the basic case here, then the basic example would be the case when D is a ball of radius r, and this mu is a constant times the delta function at 0. So then this identity here is just the mean value theorem. If you put k equal to 0, then this W will be harmonic. And this identity is saying that the integral of a harmonic function over a ball is equal to constant times the value of the harmonic function at the origin. It's maybe less well known that the mean value theorem also holds for solutions of the Helmholtz equation. But in that case, this constant C will depend on K and R, and this constant could actually be positive, 0, or negative. Okay, but it turns out that in the case K equal to 0, there's a big theory of these quadrature domains in complex analysis. You have many examples, and one can extend those also for non-zero Ks. And these quadrature domains include some domains with boundary singularities, such as having inward cusps or double points. So let me give you an example here. So this is a cardioid domain. So it has one point here where you have an inward cusp singularity. And this is a quadrature domain for harmonic functions. So if you have any harmonic function in the cardioid, then the integral of that function over this domain is equal to a combination of h at 0 and the x derivative of h at 0. So in this case, the compact body distribution would be combination of a delta function and the derivative of delta function at the origin. So this kind of result shows that there are some special singularities, typically inward cusps or similar, that can be invisible. Okay, and then in the other direction, so let's assume that D is an obstacle which is invisible for some h which is not identically equal to 0. And the result is saying that then near each point x0, which is on the boundary of D, so that you have a non-vanishing condition for the incident wave at the boundary point x0, then you have two possibilities. So either this D is somehow regular near x0, the minimal thing would be C1 if this contrast F is assumed to be Dini continuous. Or the other possibility is that the complement of the obstacle Rn minus D is somehow thin near x0. So it's thin in the sense of minimal diameter, which I'm not going to define precisely, but you can think of having an inward cusp. So if you have an inward cusp singularity, then the complement will be very thin near that cusp point. And also you have higher regularity if this H is CK alpha or real analytic, and you are in the situation A, then the boundary of D will be CK plus 1 alpha or real analytic. And this kind of result is an application of a free boundary regularity result. And this was proved earlier for Lipschitz domains D by Ciacconi and Vogelius. So for Lipschitz domains, of course, this case B is not possible. So it's excluded by assuming that you have a Lipschitz domain. So we proved this kind of result removing this Lipschitz boundary assumption. And there are related results by Ciacconi, Vogelius, Chao, and some others. So this is kind of what you can say about the boundary of an invisible obstacle. So it's exactly the same kind of behavior as you have for the free boundary in an obstacle problem, if you assume this non-vanishing condition for the incident wave, which these results always have. Okay, so these are some of the main results. And if you compare to these earlier corner scattering results, then these free boundary methods, they apply to very general sets D, general obstacle, not just curvilinear polyhedra, like in some of these corner scattering results. And they can apply in any dimension, not just n equal to 2 and 3, like in some of these early results. And they allow you to get an idea for some kind of characterization of what the invisible obstacles can look like. But on the other hand, all of these results require this positivity condition. So the incident wave U naught needs to be positive on the boundary of D. And this is actually a restriction, which is not present in these corner scattering results. And actually some of the hard work in the corner scattering result is to prove these results without assuming this kind of non-vanishing condition. And this condition is somehow non-trivial, because if you have let's say any real value solution of the Helmholtz equation, then typically it will have many zeros. For instance, if you look at dimension 1, then this equation is U prime prime plus k squared U equal to 0. So solutions will be like sine of kx, and these will have lots of zeros, and the zeros will be quite dense if k is large. So typically these incident waves, if they are real value, they will have many zeros. So even finding an incident wave satisfying this condition on the whole boundary of D is non-trivial. But one can show, for instance, these results with Cohen and Chagolian. So if D is a bounded Lipschitz domain, then you can always find an incident wave and even a Hergos wave, which is positive on the boundary of D. Okay, so I think this concludes the main results. Any questions at this point?
Mikko, one question.
Yes.
This is Fiora. So, I mean, you have the assumption that K is not a Dirichlet eigenvalue, right? For the result here. Okay.
Yes. Yeah. So this was in this slide assumptions. So yeah. So that's needed in maybe not all of these results, but at least most of these results. So, yeah, for instance, if K is a Dirichlet eigenvalue, this theorem 4 can fail. Right. So you cannot find a positive incident wave on the boundary of D. That's right.
But yeah, the interest is that it's not a transmission eigenvalue, right? So then the restriction is not that bad.
Yeah.
Yeah. Thank you.
Yeah, but yeah, thanks very much. But yeah, so somehow this positivity assumption is the one which somehow should be removed in order to really improve these results, because it might easily happen that an incident wave can vanish at some boundary point of the obstacle, but at the moment these free boundary methods do not seem to be able to handle that situation. That's a very interesting question. Yeah, thanks. Other questions? Okay, so let's go to the final part, which is about the methods. And here I thought that, because I think there may be people in the audience who are interested or have worked on the Calderón problem and use complex geometrical optics solutions. So I'm going to show a little bit some of the methods in these corner scattering results, starting from this paper of Blåsten, Päivärinta, and Sylvester, and some small variations that I did with Päivärinta and Vesalainen. So these are using complex geometrical optics, CGO solutions, and Laplace transforms. So let me try to indicate how this goes. This will be a little bit technical, but please bear with me. So omega is a bounded domain. For simplicity, let's assume the frequency k is 0, and the potential q is equal to h times chi d, where now this d has a special form. D is the intersection of a cone and the unit ball. So you have a picture like this. So your D here is this colored thing, and then you have a corner singularity. So this C will be the full one-sided cone. And this H will be a contrast, which is non-zero at the corner point. So we have an obstacle which has a corner point, and we assume that lambda QF is equal to lambda 0F for some fixed F, which is not identically 0. So somehow this obstacle here is giving the same measurement as empty space, and we want to derive a contradiction. Okay. So now we are going to use some methods which are familiar from the theory of the Calderón problem. So since lambda QF is equal to lambda 0F, we can use this so-called Alessandrini identity to say that 0 is equal to the integral of the boundary of lambda Q minus lambda 0F against some function W. And the Alessandrini identity that this boundary integral can be written as integral over the domain omega, and then you have the difference of the potentials, which is Q minus 0. But now Q had this special form H times chi D. So this will be just an integral over D, and then you have H, then you have the solution with Dirichlet data F, and then this W will have to be a solution. So this U naught F is the solution of Free-Helmholtz equation, or actually just the Laplace equation in this case, because K is equal to 0. And W can be any solution of the Schrödinger equation in omega. So this is different from the Calderón problem because this F is fixed. So the solution U naught F is fixed. We cannot vary that like in the Calderón problem, but we can vary this other solution W, the solution of the Schrödinger equation. And this looks like this is not so much information, but it turns out that if D has a corner point, then you can get the information out of this identity here. So we use the CGO solutions. Rho is a complex vector. Rho W has the form e to the minus rho dot x 1 plus r, where the remainder term r goes to 0 in some way when the norm of rho goes to infinity. So this is what we are going to use for W. And for this harmonic function U naught F, so it's harmonic. And so we want to expand it as a Taylor series at the origin. The origin was the corner point. And because F is not identically 0, then the Taylor series at the origin is not identically 0. This function is real analytic. So this expansion is h of x, sorry, plus order of x to the power n plus 1 near the origin, where h is a homogeneous polynomial of degree n. It will be harmonic because the solution is harmonic. So you are going to plug in these two formulas into this identity here. So what do you get? So you get the main term, which is integral over d, e to the minus rho dot x. You're going to freeze the coefficient h at 0, assume this is somehow continuous, and then you get the harmonic homogeneous polynomial capital H plus error terms. And then you're somehow going to do a blow up. So you change variables in the main term, x goes to x over rho. So this blow up thing comes up in the free boundary approach as well. So the main term becomes a Laplace transform. So it's some power of norm of rho. You have h at 0, and then you have a Laplace transform of the polynomial h times the characteristic function of the cone. So you have the Laplace transform of that at some complex vector, rho divided by norm of rho. So, okay, we assume that the contrast is non-zero at the corner point, so this h of 0 is not 0. And this capital H is also not identically 0, which implies that the main term has size rho to power minus capital N minus n. So now we are going to prove that these error terms here somehow decay faster with respect to rho. So the error terms are bounded by norm of rho to power minus capital N minus delta. And this is going to imply that the main term or has to be 0, or that this Laplace transform here has to be 0. So this can be done by some LP estimates for the complex geometrical optic solutions, which are not so easy because this potential has low regularity. And if you need LP estimates for large P, then that is not so easy. But in low dimension, you can use the fundamental Calderón estimate of Koenig, Ruiz, and Zog to do this. So you get the vanishing of the Laplace transform. And now if you go to this case of my paper with Päivärinta and Vesalainen, in 2D, harmonic homogeneous polynomials are very simple. So they are just these complex exponentials. You have some coefficients A and B here. And this cone will also be very simple. So just the points where the angle theta is less than some epsilon. So it turns out that this vanishing of the Laplace transform will become a linear system for these coefficients A and B. And you can compute its determinant, which will be non-zero if the C has angle less than 90 degrees. And this is going to give H is identity equal to 0. So this is just explaining some of these results on the corner scattering literature. And you can see that these are already non-trivial. So then let's go to the new, the free boundary approach. So for simplicity of presentation, let's assume that the boundary of these Lipschitz frequency is equal to 0, Q is equal to H times chi d, and this single measurement lambda QF is equal to lambda 0F for some fixed F. And now you let U and U naught be the solutions of the Schrödinger equation minus Laplacian plus Q of U equal to 0, Laplacian of U naught equal to 0. And U naught have the same Dirichlet data F. And then if you look at this star, this is saying that the normal derivatives of the solutions are going to be the same. So d nu U is equal to d nu of U naught on the boundary. And now you can see, if you're familiar with the interior transmission problem, this is almost the same as that one. So the difference is that we want U and U naught to be solutions in H1 instead of L2. Okay. And now, because this potential Q vanishes outside of the obstacle and the complement of the obstacle is connected, then unique continuation is going to imply. So these two equations will be just the Laplace equation outside of D, and they have the same Cauchy data. So unique continuation implies that U is equal to U0 outside of D. Okay. So we can rewrite this equation here just by taking the difference of U and U naught. So W is equal to U minus U naught. So this gives minus Laplacian W is equal to the potential times U. The potential was H times chi d. So minus Laplacian W is equal to HU chi d in omega, and W is equal to 0 outside of the obstacle. Okay. And finally, using these non-vanishing assumptions that the contrast is non-zero at the obstacle and also the incident wave, and therefore also the solution U will be positive, then we can rewrite this equation as minus Laplacian W is equal to F times the characteristic function of the set where W is not equal to 0. So this you will have in some neighborhood of the boundary D. And if you look at this equation, so in this equation, you don't have this set D anymore. So you only have this solution W. And this is typical of these equations in free boundary theory. So this kind of equation, minus Laplacian W equals F times the characteristic function of the set where W is not equal to 0 in some neighborhood U of the boundary. So this appears in so-called no sign obstacle problems. The free boundary is the set the boundary of the set where W and its gradient vanish, and in this case is equal to the boundary of the obstacle. And the idea in this free boundary theory is to study properties of the solution W and use those to conclude something about the regularity of the boundary. And the main way of doing this is based on so-called blow-up analysis, which was somehow systematically used by Caffarelli in these free boundary PDE questions. And originally these ideas came from geometric measure theory and minimal surfaces. And there's a very large literature on these methods. And there's a textbook by Petrosian, Shagolian, and Uraltseva, which contains most of what is needed to deal with this question. So at this point, somehow, once you have rewritten your equation like this, then these free boundary methods are starting to take over. So in the last couple of minutes, let me just try to give you a quick idea how one proves this free boundary regularity by using these methods. Okay. So you need to, you want to know as much about the solution W as possible. And the first step is to prove optimal C11 regularity of the solution. And this is non-trivial because if you look at the right-hand side, it has a jump discontinuity. So the right-hand side is in L infinity, but it's not continuous. And the kinds of estimates that you would like to use, the Calderón-Zygmund estimates for this problem, they fail at L infinity. So you don't get this easily. You have to use some special property of this equation, basically the vanishing of the solution W outside of the obstacle to get the C11 regularity. But this is well understood in the free boundary literature, and you get these scale invariant estimates that the second derivatives W are uniformly bounded. And the next step is to start to do a blow-up analysis. So you assume that 0 is a boundary point, and then you look at the sequence of rescaled solutions. This W lambda J of X equals W of lambda J X divided by lambda J squared in the unit ball, where these scalings lambda J go to 0. So somehow you look at tiny neighborhoods of the free boundary point, and then you blow up that tiny neighborhood into the ball of radius 1. And because you have good estimates which respect the scaling here, these W lambda J's will converge to some limit, which is a C11 function. It's called the blow-up solution. So here's a little picture. So this is a blow-up procedure near the cusp point of a cardioid domain. So here you have a boundary point, which is an inward cusp. And then you look at these smaller and smaller balls, and you blow up each of these balls to radius 1. And then in the limit, you will have a blow-up solution, which here is denoted by U0. Okay. And the next step would be you want to classify all the possible blow-up solutions. And it turns out that in this obstacle problem, and here you are starting to use the fact that the incident wave is non-vanishing, you only have two possibilities. So either the boundary is regular, and the blow-up solution is, after some normalization, 1/2 times xn plus squared. So you call such a boundary point regular. Or you have these inward cusps or some related things where this blow-up solution is a second-order homogeneous polynomial. So this would be a singular point. And then the final thing would be to use the properties of these blow-up solutions and pass to some properties of the original solution. So in particular, you prove directional monotonicity of these blow-ups near regular points. And this allows you to prove the regularity first Lipschitz, then C1, and then real analytic, if the regularity of the contrast allows it over the free boundary. So these two steps require the non-vanishing condition for the incident wave. And it's not well understood what happens when you don't have this condition. And it turns out that there are some free boundary problems where if the non-vanishing condition fails, then you actually get some corners which do scatter. So these are called unstable obstacle problems. But it seems that in this problem coming from inverse scattering, everything suggests that you should have this kind of dichotomy of these boundary points. But that remains to be proved. Okay, but let me conclude here. Thanks very much.
Thank you very much, Mikko, for the very nice talk. Thank you very much. Are there any questions or comments, please?
I have a question here. Jian Liang.
Okay. Yes, hi.
So, okay. So, there's kind of two questions. One is that you at the beginning there's so-called K quadrature domains. So,
Yes.
I imagine that there are some quadrature points associated with such kind of problem. Because I'm computational mathematician, so numerical quadrature we always play with those things. So
Yes.
does those kind of quadrature point can be used for designing like a numerical quadratures?
Yeah, so that's actually where the name comes from. So as you see from this formula here,
Yeah.
this is saying that if you have a harmonic function in a Cardian domain, then somehow you can evaluate its integral by this kind of some kind of quadrature. So you take a combination of point values of h and its derivatives. So somehow that's where the name comes from, and there's a big theory on this in complex analysis. I don't know if this is used computationally, but at least that's where the name is coming from.
But these are okay. So my imagination that those kind of things have a universal property. For example, can be widely applied to various functions, or just only for such kind of like the harmonic function and specific for such kind of domain.
Yeah, so
so
I've seen these kinds of things for also for analytic functions and for harmonic, subharmonic, superharmonic functions. And now what we do here is that we do it also for solutions of the Helmholtz equation. So this is the kind of situation. So the idea is that that this quadrature domain identity is some kind of extension of the mean value theorem. So in any situation where you have a mean value theorem, you might ask if there are some more general quadrature domains which have satisfy similar identity. So maybe that's the best answer I can give to your question.
Okay. So another question is how stable this kind of formulation or inverse formulation. For example, if I'm interested to design such kind of domain, how stable such kind of shape towards related to like given data.
So I'd say that these kinds of problems are quite unstable. So if you look at this this work here by Blosten and Liu, so they have several papers on this topic, and they study the stability issue. And these single measurement inverse forms, they are quite unstable typically.
Okay, thanks.
Yeah, thanks very much for the questions.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments? Okay, if not, thank you very much, Mikko, for the very, very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you.
Thanks.
Thank you very much.